So we're talking about radian measure and circular functions. And if we think back to what I was telling you about the story about the salt ponds in the San Francisco Bay Area, right? You want to restore these, you start getting tidal data, and you look at this, and you see a periodic function. It's a really nice periodic curve. It looks like a sine curve should fit it, but there's a problem. Right now, what's my domain for sine and cosine? What do I plug into it? I plug in degrees, right? I plug in angles, and what do I get out? Ratios. So this is nice and periodic, but I know it's hard to see. This isn't measured in degrees. What are they measuring the time, and what's this independent axis? Time, right? This is a date. So this is time, and this is feet above mean sea level. And so, right now I can't plug it in because this isn't measured in degrees. And in fact, lots of stuff in the world is not measured in degrees, but has a periodic nature. So we come to this problem of, we want to use a periodic function. I want to fit a curve to it, but it doesn't have the right domain. I don't have degrees. So we come up with this thing of radians. All right, so it's not an angle, but we should be able to fit a curve to it. So what we do is if I take a circle, and I imagine this as my number line, all right, and I start wrapping the number line around it. So I take the 3, and it goes there. I wrap the 2, I wrap the 1. So I'm taking a number line, and I am wrapping it around the circle. What's that length all the way around the circle called from geometry class? Circumference. So really we're talking about the circumference. So we're going to try to build this graph, this periodic function, using the idea of a length. Because we measure lots of things in length, and that's a little bit more general than degrees. Okay? So that's the big idea. We okay with the big idea? All right. Let's make it complicated. So we're going to use radians, this thing called radians. Basically, we're wrapping that circle, and we're going to look at a circumference. Okay. So a radian measure is defined as the arc length over the radius. Okay? So it's the length of the arc divided by the radius. If I was to give you a geometry problem, and I wanted to know the arc length of A defined by this sector. Can anybody think back as to how you would do that? How would you find that arc length? How do you find all the way around? Good. Okay. How far is all the way around in degrees? 360. All right. Well, it turns out that it's just proportional. All right. It's proportionally 23 degrees over 360 is my arc length over 2 pi r. So and it makes sense, if this was 90 degrees, we'd expect the arc length to be a fourth of the whole thing. If it was 180, we'd expect it to be a half of the whole thing. If it was 360, it's the whole thing. If it's 23 degrees, it's this proportion of the whole thing. Okay? Keep that in mind. And what's going to be nice, and where we get this idea of the unit circle, is if I made the radius 1, then the radian measure is just the arc length. So that's where our unit circle is going to come from. We have the denominator drop out when we set it equal to 1. All right, so let's start with the circle. We're going to call our axes U and V. And I'm going to get a point, and I'm going to have an arc length. I'm going to draw my triangle. So we're trying to build this link between what we know about triangular trigonometry and now this idea of an arc length. So that's u and that's v, according to my general point, u comma v. And what we're going to define is this u is cosine of x, where x is the arc length. And v is going to be sine of x, where x is the arc length. So we're going to define those that way. The big question becomes, why is that true? Why can't we just make this leap between now we've been talking about a triangle and an angle, and now suddenly I have an arc length, and we're saying that cosine of x is actually u, and sine of x is actually v. Well, let's think about what the proportion would be. X over 2 pi r is theta over 360. It's this picture. Okay? I just have variables. I don't have numbers on it. Not judge if you agree with that statement. Does that sound true? It's just proportional. This arc length over the circumference is equivalent to the angle over 360. If the angle was half of 360, the arc length would be half the circumference. If it was 90, it would be a fourth. All right? If I solve this, and if I get x over r, multiplied by 2 pi, I get this. Now, if my radius was 1, we have this fact that 2 pi and 360, what's special about those? It's the same thing. All right? 2 pi radians and 360 degrees is the full circumference. It's the same thing. So that's a fancy way to write 1. And I get x over r equals theta. Okay? If I take cosine of both sides, I get that. So cosine of this has to equal cosine of that because they're equal to each other. Well, if r is 1, this becomes cosine of x, right? And then what's cosine of theta if you just look at your triangle? U over r, and if r is 1, what does it equal? U. So what we're going to get, if we are on a unit circle, cosine of x is cosine of theta, and all of that equals u. So that's a big leap. What we actually just did is that this arc length, cosine of the arc length, is the same thing as cosine of this angle, and this angle on the unit circle, cosine is u. That's a big mathematical leap. Because what this tells us now is that this, if I use this idea of an arc length, this is my cosine value, this is going to be my sine value. They're equivalent. You still okay? That's a big idea. We good? Yeah? Excellent. So that becomes cosine of x, and x is an arc length. It's not an angle anymore. We've gone away from angles. I know that that's scary and that's weird, but we have an argument for why it's true. There's my sine value. Okay, here's why we care. So what are the units on my radians? Well, if it's an arc length over the radius, what are the units? What could you measure arc length in? Centimeters. And what would the radius be measured in? Centimeters. And then centimeters over centimeters, those cancel. And you get what's called a length per length, which is a dimensionless number. Sounds weird. All it means is that the units don't matter. If you plug in centimeters, you're going to get centimeters over centimeters, they cancel. If you plug in time, you're going to get time over time, they cancel. So what you have with radians is you have a way to take that tidal data, where time is what you're plugging in, and you can plug it in now, because we have a domain that's dimensionless. which is really powerful because there's no restrictions on it. If you have a periodic function, you're going to be able to plug it in if you use radian values. If you're using degrees, you have to plug in degrees. You have to plug in angles. Okay. So this can be any units that I want, which allows us to take sine and cosine to the stock market, to environmental studies, to different periodic natures. So it's a big jump for us. I said it was huge. All right. So the question is, how do we go back and forth? Okay? How do I convert? So if I look at this point on my circle, if I was to measure that angle in standard position, so if I start here and I rotate, what is my degree measure? 180. If I had a unit circle, and this is 1, what does that measure in terms of an arc length? Pi. (180 degrees) pi radians. So what this allows us is a conversion factor. Okay? If you had 12 inches equals 1 foot, it's true that 12 inches over 1 foot is 1. Right? If you divide both sides by 1 foot. This allows you to convert 23 feet times 12 inches per 1 foot. Cancel, cancel. You get your answer in inches. So if I want to go degrees to radians, I'm going to multiply by pi over 180 degrees. So if we think about the goal problem, 23 degrees in radians, I multiply by pi radians over 180 degrees. Those of you that have taken physics or are taking physics or even chemistry, if you look at your units, you have degrees times radian over degrees. Those cancel, you're left with your radians. So I get 23 over 180 pi radians. If I wanted to go the other way, if I had radians and I wanted degrees, what do I need to do to this fraction? Flip it. So radians to degrees, I flip it. I have radians, I want degrees, I want to cancel the radians, I flip it over. Alright? Again, these are fancy ways to write the number 1. These are equivalent. And that's the only reason why I can multiply by this number, because I have to multiply by 1. That doesn't change my value, it just changes my units. Just like taking 2 feet times 12 inches over 1 foot is 24 inches. That's the same measure, it's the same distance, it's just a different way to think about it, a different measurement of unit. Okay. That was a lot. We okay still? Yeah? Excellent. So the take-home message is radians allow us to have a dimensionless domain. It allows us to plug anything we want in, so now we can take anything that's periodic, we can fit a function to it. All right. What I want us to do then